Hello everyone, this is lesson 5 and today we're going to be looking at how to convert from general form to standard form. Again, your textbook calls it standard form, but anytime you see that, we are going to change that to vertex form. Basically, we're moving from ax squared plus or minus bx plus c, y equals to, into y is equal to a times x minus p squared plus q. Again, both forms have its advantages. For the general form, in this classic quadratic form, the easiest thing is if we were to make x equal to 0, then we know that these terms go away and the y-intercept must be equal to just whatever c is. Whereas in the vertex form, the p parameter and the q parameter are automatically the coordinates of the actual vertex. Okay, so both forms have its advantages. And we're going to be using a method called completing the square to move from quadratic form to vertex form. Where does the term completing the square come from? We're saying, hey, look, if we've got these two terms, okay, we're just going to look at the first two terms in a general form. If we're able to change that to a minus b all squared form, then we can convert it. Okay, so that's what's called completing the square. We're taking two separate terms and we're trying to force it to become a perfect square. So how do we do that? Okay, first let's just have a quick refresher on what perfect squares actually are. Can you take a moment and just pause the video to see if you can expand these examples given here? Okay, pause the video and I'll show the answers here. I hope that was a quick refresher. Just looking at the last two here, you should be comfortable now with the pattern. We always have x squared. The middle term is 2 times your last term and your first term, so 2ax, plus the last term is a squared, or your second term all squared. And if we have a minus sign, then we have x squared minus 2ab, or in this case 2 times a times x, plus, okay, that last term is always a plus sign, plus again a squared. So note what we are actually doing with these values each and every single time, because we're going to be going backwards, and you've done that practice before, okay, going backwards from the trinomial form into the perfect square form. So we're going to do that practice here. Again, pause the video and try this one on your own. I'll show the answers here in 3, 2, and 1. Here are the answers, and note where I'm getting each of these second terms. So for example, that's plus 3. I first took the 9 here, I squared the 9 to get positive 3. To confirm that these are actually perfect squares, I took the middle term's coefficient and divided that by 2 in order to get 3. And I did the same for each one here, so you can go ahead and have a look at the rough work by pausing the video. The reason I am doing that, again, I'm just going backwards from what we did earlier. I saw that a, we had to square it, and that we took the coefficient of the first term and the last term and multiplied by 2, and that gives me 2a times x. Okay, so going backwards, I'm just doing the opposite. Let's say in example C here, we are not given the last term anymore. What would this last term have to be in order for this to be a perfect square? So we're thinking now, okay, if I've got 2 here, I knew from my previous exercise, I took the negative 4 and I divided it by 2 in order to get negative 2, and then I have x minus 2. Okay, so let's just go ahead and do that. I take 2 divided by 2, that gives me 1. So I should have x plus 1 to the power of 2. But how does this help me determine the last value? Again, let's go to our previous example. We have negative 2 here. Even though in this case, I actually have square root of positive 4 and I got positive 2, I don't know that this is a positive. If I have negative 2, so going backwards here, what's happening here is we're taking the 2, or negative 2, we're squaring it to find that this is 4. So we're going to do the same thing. We're going to take the 1, we're going to do 1 squared to get 1. So that means the last digit here must be 1. Let's try another one for an example. My second term here is -3. So if I do -3 divided by 2, well, I get -3 over 2. Let's keep it that way. Now I want to square it to find out what the C value is equal to. -3 over 2 squared gives me +9 over 4. That means the square form of this function or equation must be x squared minus 3 over 2 to the power of 2. All right, let's try 2 more examples. I'd like you to pause the video and you try these on your own. I will now show the answer here in 3, 2, and please make sure you've tried it on your own before you start. Pause the video. And 1. Here we go. Check your work. Did you get it? Awesome. So here's a little bit of tip here for completing the square. What we did here is we had x squared plus xb, and we found for that very last term here, we had to add half of the coefficient of x. Okay, so 81 here was half of 18 all squared. So half of 18 gave us 2, gave us 9, and then 9 all squared gave us 21. So half of the coefficient of x to the power of 2. We can write it in this form if we want, saying that b is the coefficient of the middle term. And this one here becomes the C value in your general form right here. And this would be if we were to move it to vertex form. Okay, so in vertex form, this is the new part that we are adding in. Okay, so how does that help us in actually transitioning from this general form into vertex form? Let me just show you an example here, and then we'll follow these particular steps afterwards. Example 1 on page 326, it gives us this equation, and we want to write this in completed square form. In other words, vertex form. And we want to start just by making this a little easier for us to fill in some new numbers. Let's look at this as x squared plus 10. We're not going to completely forget the plus 16, but we're going to leave it on the side. Okay, so I'm going to draw a big bracket to say this is what we are working with right now, and we're going to move the plus 16 to the outside. We'll deal with that, I promise. But we're wondering here, what do we need here for our plus c value in order for this highlighted section to be a perfect square? Because right now it's not. Okay, our goal is to make it a perfect square. Let's take our b value. B value here is 10, and we're going to take half of the b value, which gives us 10 over 2, which is 5, and then we're going to take half of the b value all squared, so that gives us 10 over 2 all squared, which gives us 5 squared, which is 25. I'm writing out all of these steps so that you can see, hopefully we're just skipping forward to this step here. That gives us x squared plus 10x plus 25, and then on the outside of the bracket plus 16. Okay, but we know this is an equation. In order for these two equations to still be equal to each other, I can't just add a 25. That's not allowed, okay? Every time I add something, I also have to subtract the exact same thing. So the next thing we are going to do is minus a 25 as well. And you might be thinking, okay, well, what's the point? If we're adding 25 or we're minusing 25, they cancel out. So why do I have to do that? You are doing that because by adding a 25, you now have 3 terms here that actually does form a perfect square. I'm going to ask you to just look at these 3 terms and ignore the negative 25 and plus 16. As you can see, my coefficient in front of the bracket is just 1. So I can actually just drop the bracket. The bracket is not doing anything for me. Instead, I'm just going to look at my 3 terms. I know that these highlighted 3 terms form a perfect square of x plus half of the b value all squared. I can replace half of this b value with the 5 that I calculated over there, so x plus 5 all squared. And then this negative 25, okay? Again, we're just dropping the brackets here, so I actually have minus 25 still, and plus 16. And that's something we can simplify. And we're finished now. We have the completed square form or the vertex form. Just two pieces of information though that we can pick out from it, which is now the P and the Q value. Okay, so from your general form, you now have a vertex form where it's very clear for you what the P and Q values are. My P value here, I have x plus 5, which means P must be -5, and Q is a -9. Give me coordinates of the vertex, -5 and -9. There you go. So if you had to algebraically determine the vertex of this particular function, you would use this complete square form to find the vertex form and determine the coordinates. But at the same time, remember, in the original general form, it's also very easy for you to determine the y-coordinate of the intercept. So actually, two pieces of information I have now about this equation. I know the vertices, or the vertex, sorry, singular, and I also know that the y-intercept here is equal to 0, +16. The second example here is very similar. I won't do the full solution in this video. I'll attach a second video and you can check the solutions on OneNote. Let's now move on to page 327. We're going to be converting this equation here to standard, or in our term, vertex form by completing the square. And we're going to find out whether or not the graph has a maximum or a minimum value and state what that particular value is. Remember, that maximum or minimum is simply your vertex. If it opens upwards, then we have a minimum. And if it opens downwards, then we must have a maximum. Notice something different about this equation, because this time we are starting with a coefficient in front of x squared. Whenever you have this coefficient in front of x squared, we're going to do things differently. What we're going to do is factor out the coefficient 3 from both the first term and the second term. But we're going to leave the last term alone. Okay, we're going to leave the 20 alone. You'll see why in our example. So let's start with f of x is equal to, I'm going to factor out the 3 here. We have x squared minus 6x. Now, even if, so in this case, 18 divided by 3, perfect, it gets a 6. But even if it's not an integer, if it's a fraction, you still have to do this step, okay? So in your homework, you'll see there's examples where you get a fraction. Just do it, that's completely fine. Again, I'm going to leave an empty space to figure out what I need to fill in there in order to get a C value here that allows me to have the perfect square. And then I'll add 20 over here. Okay, so what does my plus C have to be? Well, let's take the middle term again. Middle term, -6 divided by 2, that gives me -3. -3 all squared, this gives me 9. So that C value must be 9, plus 9. And if I add 9, I have to minus 9 as well. Now this time, just be careful here. Again, these 3, great, forms a perfect square trinomial. But that 9, I have to remove it from inside the bracket and I have to combine it with a plus 20. But I cannot just do -9 plus 20. Be super careful here. Why is that? Because this is not just -9. This is 3 times -9. Okay, so in my next step, I have to do 3 times -9 and then I add 20 to that. So let's take our perfect square trinomial. I'm making that x minus 3 all squared. And then 3 times -9. And that simplified gives me -3, -7. Remember in my original form, this is already x minus p. So that means my vertex here is p is equal to 3, q is equal to -7. The question is asking us for a maximum or minimum value. So we can see that this graph opens upwards. That's positive, opens upwards. That means I have a minimum value of -7. All right, that's it for this video. In the next example here, I will put this solution up on OneNote and another video if you like to see another example. There's a review of these steps from the second example on page 327. Maybe that will help you as well. That's it for this lesson.